This video will cover in class 13, which is day number 2 for standard 4. The focus today is on reflections. In order to reflect, since we are using the coordinate graph system, we need to remember how to graph certain lines from our algebra days. So the lines that we're going to focus on using are lines that are y equal to a number, x equal to a number, y equal to x, and then y equal to negative x. So we're just going to take a quick algebra review here at the beginning to make sure that we're rock solid on what these different lines will look like. So what I like to do is I like to think about places on the graph where y is equal to 2. So if I'm at the origin, that means 0 for y. If I'm going to where y is equal to 2, hopefully your instinct is to go up 2 on that y-axis. But that's not the only place where y is equal to 2. If I slide over to the left, but I still go, or that's the right, sorry. If I slide over to the right, but I still go up 2, that's another place where y is equal to 2. Or if I slide to the left, but still go up 2, that's a place where y is equal to 2. As well as all of these other points, both on the grid line and between the grid lines, as long as I've moved up 2 full boxes on the graph. So when I end up graphing, I don't need to put all of those points down in order to graph, but I do need to show that y equals 2 is a horizontal line that passes through the y-axis. Now that's going to mess with your brain a little bit because when people see y, they assume it needs to be vertical, like the y-axis, but it's not. It's horizontal and it passes through the y-axis and shows all of the places on the graph where y is equal to 2. X equals negative 5 is similar. So if I'm at the origin, to get to the first place where x equals negative 5 that most people think of, 5 boxes to the left. We'll take care of that. But I could also be a little bit higher up on the y-axis and still travel over 5 boxes to the left. Or I could be lower on the y-axis and travel 5 boxes to the left. Anywhere along that vertical line that passes through the x-axis, x will be equal to negative 5. So y equals a number is going to be horizontal. X equals a number is going to be vertical. For this equation, y and x need to match. So if I go to a place like 0 for x, I have to keep my y 0. So the ordered pair would be 0, 0. So the origin will work. If I move to a place where x is, let's say, 4, then that means y also needs to be 4. Or if I go to where x is negative 3, y also needs to be negative 3. So this line is going to be a diagonal line that goes directly through the corner of each box. Officially, it has a y-intercept of 0 and a slope of 1. So we start at 0, 0, and we go up 1 to the right 1, up 1 over to the right 1, or down 1 over to the left 1, over and over again. So y equals x will look like a diagonal line, directly diagonally through one box at a time. Y equals negative x is similar, but this means that y is the opposite of x. So if x is 0, the opposite of 0 is just 0. But if x is 3, the opposite of 3 is negative 3. So when x is positive, like 3 or like 5, then y is actually negative, like negative 3 or negative 5. The same thing happens if x is negative. If x is negative 2, the opposite of negative 2 is positive 2. If x is negative 6, the opposite of negative 6 is positive 6. And so this line is going to be diagonal, one box at a time, but the opposite direction. Y equals negative x. Those types of lines are going to help us as we move into studying our next transformation a little bit more specifically. So the focus today, clear that up a little bit, is on reflecting. So like we said yesterday or whenever in class 12 happened, A transformation that flips a preimage over a line of reflection is what we're talking about when we talk about reflections. That means that the image is going to be like a mirror of what we started with, but it will also be an equal distance away from the line as the preimage was. And so what's going to happen is if our preimage is really close to our line of reflection, the image will be really close. If the preimage is really far, then the image will be really far. So the best way to do this is to just practice. We have preimage triangle ABC already graphed on this first example, and our goal is going to be to reflect over the x-axis. We always want to show the line that we're reflecting over. So our x-axis is this horizontal axis right here. So I'm going to highlight that. I'm going to draw over the top of it. Try to do the same thing in your notes. I know if you're using pencil, it's hard to make that line show up, but do your best. And then we're going to use the idea that this preimage is going to flip over that line. So it's going to end up down here somewhere, but it needs to be an equal distance away from the line as this preimage. And so the best strategy that I have for that is to look at each vertex at a time, figure out how far it is away from the line of reflection. So this is 1, 2, 3, 4, 5 boxes away. And then just keep right on counting. 1, 2, 3, 4, 5 boxes away on the other side to place that C prime point, that new image version of C. You can repeat that with the next vertex. So let's figure out how far away A is from that line of reflection. 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes away from the line of reflection. So we need to go 9 boxes away on the opposite side to place our A prime. If we take care of that last vertex, point B, 1, 2, 3, 4, 5, 6 boxes away from that line of reflection. So we need to go 1, 2, 3, 4, 5, 6 boxes away on the other side. And then if we connect those 3 vertex points together, we should end up with a reflected version of our preimage. What used to be on the top has now flipped over to the bottom. What used to be close to the line of reflection stayed close, and what was farther away from the line of reflection stayed farther away. But it didn't move at all left to right. It didn't translate like our previous transformations. It just made a mirror image of itself on the opposite side of the line of reflection. Let's do another example here, but this time we're reflecting over y equals 3. So we need to find a place on our graph where y is equal to 3. So if we start at the origin, that would mean go up on the y-axis 3 boxes. And then remember, we could go a little bit to the right, and y would still be 3, or a little bit to the left, and y would still be 3. We just wouldn't be able to go up or down because then y would change. So y equals 3 is going to look like a horizontal line through the y-axis at 3. So this preimage is all below the line. So when it reflects, it's going to reflect up here above the line. A is the point that's closest, so I'm going to start with that one. It's 1, 2, 3 boxes below. So A prime is going to be 1, 2, 3 boxes above. C is 1, 2, 3, 4, 5, 6, 7 boxes below. So 1, 2, 3, 4, 5, 6, 7 boxes above for C prime. B is 1, 2, 3, 4, 5, 6 boxes below. So 1, 2, 3, 4, 5, 6 boxes above. The same distance, but on the opposite side of the line of reflection in order to get that reflection image graphed. Example number 3 switches up the line of reflection again, and it makes it an x equals equation. So if I'm at the origin and I want to find a spot where x is equal to -1, I'm going to move 1 to the left, but I could also go up and still be 1 to the left, or down and still be 1 to the left. So x equals -1 is going to be a vertical line through the x-axis at -1. C is the closest one to my line of reflection. It's only 1 box away. So C prime is going to be right on the other side, just 1 box away. A is 2 boxes away, so A prime will be 2 boxes away on the opposite side. And then B, be careful here, make sure you're counting each box even though it's kind of squished in there. 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes away. So 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes away on the opposite side. Be really careful with your counting. If you need to double count or check it, please do. It's not complicated. It's just that you can really get off with your counting pretty easily. And so that triangle flips over to the other side, an equal distance away from that line of reflection. Okay, in example 4 and 5, we're going to run into our diagonal lines. And so that's going to make counting a little bit more complicated. So first things first, I'm going to graph y equals x. That's where y and x are always the same. So that means I've got points like 0, 0, 1, 1, 2, 2, 3, 3, or -1, -1, and then -2, -2. So this long diagonal line that you need to really precisely graph, because if we're going to count based on this line, it needs to be in the right location. You can't just eyeball it. You really precisely need to graph it through the corners of each of those boxes. And so I don't know if you noticed this or not, but when I was doing my reflections, if there was a horizontal line, I was counting vertically to reflect. If there was a vertical line, all my counting was horizontal to reflect. So because this is a diagonal line, I'm going to need to count diagonally in order to reflect, which is really tricky. So we want to be careful with our counting. Now, something interesting is happening here with point P. P is touching the line of reflection. So it is 0 boxes away from that line, which means that that same exact location is going to be P prime. That point is not going to move when the reflection happens. If we look at point M, we're going to count diagonally towards the line. So we've got 1, 2, 3 diagonal boxes. We keep going on that same diagonal path, 3 diagonal boxes on the other side. So M prime is the same distance away diagonally from that line as point M was originally. We're going to do the same thing with L, but it's going to be a little bit trickier for your brain because you're not going to follow this diagonal path. That's the side of the triangle. You need to go diagonally through 1 box at a time. So 1, 2, 3, 4, and then a half box. Right on the other side of the line of reflection is your half box, and then you need 4 more to match that distance. So sometimes when you're counting diagonally, you don't end up with a full number of boxes. That one was 4.5, so I need to go 4.5 on the other side to land at the appropriate location, L prime. So if I connect those 3 points, it's going to look a little bit different, but that's because the reflection is happening diagonally. And so sometimes it helps if you turn your paper and you make that line of reflection look vertical. Now it looks like those would just fold up and match on either side of that line. It makes you feel a little bit more confident about your reflecting. Sometimes it looks a little bit weird when you're just looking at it. Okay. Example 5 is going to be similar, except the line is y equals -x. So that's where y and x are opposites, which takes that diagonal line and it just flips it the other direction. It would have a negative slope instead of a positive slope. But again, really careful graphing is important because if our line of reflection is in the wrong spot, then when we count to that line, we're not going to be counting the appropriate distance. If we start at L, we're going to count back towards that line diagonally. 1, 2 diagonal boxes. So 1, 2 diagonal boxes on the other side. For P, we're going to do the same thing. 1, 2, 3.5 diagonal boxes. So we take care of the half right away, and then 3 more full boxes for P prime. And then this one's going to be the farthest distance, and this side is going to try to distract you. So make sure you're counting 1 diagonal box at a time. 4, 5, 6.5. So there's the half, and I need to go 1, 2, 3, 4, 5, 6 more. Now, if you look at your triangle, this one is kind of nice because you can kind of look at some features to see that something good has happened. M and P were straight horizontal from each other when we started, and they ended up being straight vertical from each other when we ended, M prime and P prime. That's a really good sign that we kept everything nice on a diagonal path, and we didn't get off of that count at all. All right, the last thing that we have to do here in terms of our examples is to describe what's happened. So there is a pre-image right here, the shape without the primes, and there's an image, and our goal is to describe what's happened. Now we can tell this is not a translation because if it was, M would have stayed on the left side of the shape, and instead M is flipping to the right side of the shape. So that means we're flipping this pre-image over to create the image. We just need to figure out what line we reflect it over. So if we look, we can split the distance between these two to locate the line of reflection. So if I count from M to M prime, 1, 2, 3, 4, 5, 6 boxes, that means that my line of reflection needs to be 3 away from each. I could do the same thing with P and P prime, or I could do the same thing with L and L prime. If we count into the middle, that line of reflection needs to be halfway in between that pre-image and image point pair. And that gives us a really good picture of what that line of reflection looks like. But we need to write the instructions like we've been given. So this is a translation, or not a translation, a transformation where we need to reflect over this line. So is X always the same on this line, or is Y always the same on this line? It's always 1 to the right, but it has lots of different up and down values. So this would be the equation X equals 1, where we're always 1 to the right of that Y-axis. So if we go back through and we look at our examples, let's see what a reflection does or does not do. Does a reflection change the size of the pre-image? So when we compare the pre-image to the image, it definitely looks different, but it does not change the size, and it also does not change the shape. It's the same type of triangle, it's just in a different location. So very similar to translations yesterday, we're just changing the location in a different way. Thanks for watching.